Okay, so our third lecture for chapter 5 is really going to focus on us doing some problems because I feel like we just need to be doing and applying a lot of these problems because there's a lot of different types of questions that we can see with the ideal gas law. So the first worksheet that we're going to look at is this intro, the ideal gas law intro worksheet. And so what this one is going to do is just have us practice using the ideal gas law, PV equals nRT, and how we apply it. Right? And so when we get to a problem like this one, it says if I have 4 moles of gas at a pressure of 5.6 atmospheres and a volume of 12 liters, what is the temperature? And so we want to try to set up that question. And so when I read through it, I can start to write down the information that I know. So I know at some point I'm going to need the pressure, the volume, my N, and my temperature. And so my pressure is 5.6 atmospheres. My moles is 4 moles. My volume is 12 liters, and my temperature is what we're looking for. So now I want to take my equation, and I want to rearrange it to solve for my T. And now I just need to plug it in. And so my pressure is 5.6 atmospheres. My volume is 12 liters. My moles is 4. And my R 0.082. And so sometimes you can use the 1. In this case, it'd be fine because we don't need more sig figs. You can also always use the 0.6. And now we just need to plug that into our calculator. So 5.6 times 12 divided by 4 divided by 0.08206. And so this gives us 204.7. We want to think about units there, that should be Kelvin. And if we were worried about significant figures, then we would end up with just 200 Kelvin because of the 4 moles. So the important part when you're looking at these is first to figure out what you're looking for, setting up your equation, and then also making sure that all of your units are correct. And so let's look at question number 2. If I have an unknown quantity of gas at a pressure of 1.2 atmospheres, so that's my pressure, 1.2 atmospheres, a volume of 31 liters, and a temperature of 87 degrees Celsius, how many moles of gas do I have? So I'm looking for my N. Now, when I look at this, my pressure is in atmospheres, so that's good. My volume's in liters, but my temperature, that's in Celsius. And so I need to get that over to my Kelvin. So I add the 273 to it, and so that becomes 360 Kelvin. You can put a dot there, so that way we know that that one's significant. And now we should set up our equation. And so people will start to jump ahead, and they'll just write down their equation as they start to plug it in. But I always recommend starting off with PV equals nRT and rearranging that. So we're looking for N this time, so we should get PV over RT equals N. Just because you never know when you might make a mistake, especially if it's a slightly more stressful situation like an exam. You might have done it 100 times, but we still all make mistakes. And so sometimes it's better to take that moment, refine that equation, just so you can be 100% sure. So we got our volume there, or not, we have our equation there. I'm going to erase this, make some space. And so our value is going to be 1.2 times 31 divided by 0.08206 divided by 360. And so our number of moles is 1.259 moles, or 1.3 moles when we consider our significant figures there. Now, one way to check in on some of these things is that if we're thinking about it, our pressure here is pretty close to 1 atmospheres. Our temperature is relatively close to our room temperature of our STP of 0 degrees Celsius. And so it kind of does make sense that we should be at least a little bit above 1 mole, right? And that's because we know that 1 mole of gas is 22.4 liters at STP. So that's 1 atmosphere and 0 degrees Celsius. And so this is just something to keep in mind. It's a good way to check in. That way, if you had made a mistake, let's say you have flipped these upside down, and so you had 360 times 0.08206 because you had made a mistake in your setup. You would have gotten something like 0.8, and you could be like, well, that seems a little bit funky. Maybe I want to go back and relook at my equation setup. Right? So sometimes that's why I use this 22.4. It's not that it gives me the value, it's just a good way for me to check in. Let's look at this next one. If I contain 3 moles of gas in the container with a volume of 60 liters and a temperature of 400 Kelvin, what is the pressure inside the container in ATM? So our moles is 3. Our volume is 60 liters. Our temperature is 400 Kelvin. And so we don't actually have to change anything because they're all in the correct units. Now we're looking for pressure this time. So P equals nRT over V. And so we just need to plug in our 3 moles, our temperature, and divide all of that by our volume. And we get a pressure of 1.64 ATM, or about 2 ATM if we do all the rounding. And so that's what you're doing with these. You're just practicing going through. And so there's 3 big steps. 1 is collect your data. 2 is align your units. And 3 is set up your equation. After that, you're just plugging it in and you're solving it there. And so that's how you can go ahead and start to use that. Now, remember, this only works for a gas, and generally it will say something like assume that it behaves ideally, right? Because not all gases behave ideally, and so it's just one way for us to estimate what they might do. So ideal gas law does work pretty well at low temperatures and low pressures. Oh, sorry, not low temperatures, high temperatures and low pressures. That's when it works the best. It doesn't work at high pressure and low temperatures. So you just want to keep that in mind. Now, when we say low temperature, 0 degrees Celsius is not the low temperature that we're looking at. We're normally looking at like negative 100 degrees Celsius, something much lower than that. High pressure, we're not looking at like 1 or 2 atmospheres. We're looking at like hundreds of atmospheres, so like 500 atmospheres. We're going to jump down here. We're going to look at a slightly more advanced one. So let's look at, let's say, 11. If I have 0.275 moles of the gas at a temperature of 75 Kelvin, a pressure of 1.75 atmospheres, what is the volume? Well, that's not actually any harder. Here, let's do the one above it. If I have an unknown quantity of gas held at a temperature of 1,195 Kelvin in a container with a volume of 25 liters and the pressure of 425,600 millimeters of mercury, how many moles of gas do I have? Feels a little bit more complicated, but really it's kind of the same. So we know our pressure, 425, 600 millimeters of mercury. We know our volume. We know our temperature. We just need to take this and change that into ATM. So we know that 760 millimeters of mercury is 1 ATM. So 425,600 divided by 760. We should have 560 ATMs. So that is a high pressure, but we also have a high temperature. So we're not completely going out where it might not work. And so we want to solve for N. So PV equals nRT. N is equal to PV over RT. So we have 560 atmospheres, 25 liters, 1,955 Kelvin, and our R And so we just need to plug that in. So 560 times 25 divided by 1095 divided by 0.08206. Then we get a moles of 142.76, which really comes down to 140 moles. And so that's all we need to be doing when we're trying to solve these. So that's our intro to our gases. And so go ahead and work on that worksheet. There is a key up as well. So you want to practice that. And then once you feel confident with this, whether that's by doing 10 of them or by doing 5 of them or by doing all 12 of them, doesn't matter. And then you can move on to our next video where we're going to look at slightly more advanced gas problems.